Okay. All right. Listo.
There are legs. Yeah. I don't know if it does. I would. I know what I'm saying. Yeah. As long as they slowly take you to man speak, no one. Probably. So far.
Okay, I think we are ready to get started. If you can't hear me, please let me know. I'm not sure I can make this microphone work. Usually there is something here, so we'll see what we can do today. So yeah, welcome to NLP. Let me first introduce myself. I am Anna Marasovic. I'm going to be your professor instructor this semester for NLP. I have been teaching this course already twice, and I'm researching large language models, which will be the main focus of this course. I focus on interpretability and AI-assisted decision-making, communication, creativity. In this course, we have two TAs. One of them is not a full TA, but rather half-time TA. They are, I don't think, here just yet. Nevertheless, I will introduce them. One of your full-time TA is Nate. And by full-time, I mean full-time. He's still doing research and everything. So basically, he's working 20 hours on this course. He's a fifth-year PhD student working with me, also researching interpretability of large language models. And your other TA is Raihor, who is a first-year master student. He took this course last fall, and these days he's also researching with me. We are working on agents for browsing the web. Okay, so this is the team that will help you out throughout this course. And today, basically, what I want to do is kind of tell you what kind of topics we are going to cover in this course. NLP is a very broad and very diverse field. So teaching this course can be organized in many different ways. So I want to tell you exactly how I'm going to teach it. And based on that, you can be more informed whether this is the course for you. And then we are going to go into course logistics. This time around, I decided I won't predefine how we are going to, what are we going to, cover each week, because in the past that led to me rushing the materials. So I don't know exactly what we are going to cover today, but this is the plan for today and maybe next session. Okay, are there any questions before we start digging into the kinds of topics we are going to be learning in the course? Okay. All right. So first we want to cover what is natural language processing. And I want to tell you what it is by going over two foundational questions that NLP focuses on. The first question is, in what ways can computers understand and use written forms of natural language? But what is natural language? Natural language is language that is developed naturally, organically in a community. And since most of you here are CS majors, I can give you kind of an analogy with programming languages, which are opposed to natural languages. Programming languages are defined, written with a goal in mind, unlike natural languages, which just organically develop in a community. And this means that natural language, unlike programming languages, has a lot of ambiguity. And this is the main challenge when we want to build computers that understand and use written forms of natural language. And just to show you an example, here we have John told Peter about his promotion. Let's say we want to build a program that can translate this English sentence into Croatian. Croatian is my native language. All right, let's give time for these people to sit. Everyone else, is it a little bit distracting if I keep these doors open? I can close the inner doors. Would that work better for you? No preferences? Okay, I'm going to keep them open, but if it becomes too distracting, let me know and I'll close them. All right, so I was saying that we have this English sentence and we want to build a computer program that can understand this sentence and translate it into Croatian. Here, when we are doing that, it's important to understand this pronoun his, because it can refer to either John or Peter in this sentence. So if we are translating this to Croatian, in Croatian, depending on whether his is referring to John or Peter, the translation will be different. So if his is referring to John's promotion, then the translation would be John je rekao Petru o svom promaknuću. Whereas if the his referred to Peter, then the sentence would be not entirely different, sorry, would be slightly so different. The way we would translate his would be different, and we would say, John je rekao Petru o njegovom promaknuću. So the program here needs to kind of understand which is more likely out of these two. Another example of ambiguity in natural language is having words that mean something different in same occurrence of the word, meaning something different in different contexts. So here I have two occurrences of the word basin. The Amazon basin is home to the largest rainforest on Earth, and another, she filled the basin with water to wash the dishes. Again, if I was translating this to Croatian, I would need to understand what kind of meaning of the word basin is used here. And my translation would be different. Again, without reading these two sentences as Croatian, you can see that these words look entirely different. One is nizina, the other one is umivaj onik. It's kind of hard to switch between languages. So there is a lot of ambiguity in natural language. I'm sure you can think of many, many other examples. So because there is ambiguity, the model, the program we are building to kind of understand natural language needs to do some kind of modeling of probabilities. It needs to figure out which meaning out of the two is more likely. Or it needs to ask for clarification, which is not so trivial to actually program. All this together means that unlike your programming language, where you can define it and you can build a compiler, and once you have written valid code, there is just one exact interpretation of that code. With natural language, we don't have that. We can't build a complete solution of formalizing natural language into logic. And the reasons are contextuality. So we see that meaning shifts with situations. With basing, we have in different contexts, the word basing was used differently. There is a lot of underspecification, as we have seen with the pronouns, right? Like his could refer to John or Peter in the first example. And natural language is very productive You know, we are all joking, we millennials, we don't understand how Gen Z speak because now there are all these new expressions and words that just emerge organically in this younger community. That's the exact problem. Another problem why we can't formalize language with logic, because no matter how much we try, there will be a new word that is going to appear, and the way we use it, we have used it in one way previously, and now we are using it in a completely different way. So any attempt to map natural language to logic will either lose expressivity, we will simply, simplify away richness, or it will require endless additions and patches, and it will still remain incomplete. So these are one of the biggest challenges with natural language as opposed to programming language. All right, so there is that. Remember, I started with this foundational question: in what ways can computers understand and use natural language? I told you what the issue is here. I hope you kind of have a sense of this is not trivial to achieve. And now to answer this question, how the community, NLP community is answering this question is by actually building computer programs that can or should understand and use natural language. So if you manage to build an amazing translation tool or amazing tool for question answering or whatever else, then you know that, this is the extent to which a computer program can show language understanding in this specific area of natural language processing. And this is heavily an engineering pursuit. It relies on advances in hardware. By now, most of you have heard of GPUs and how GPUs are important for this line of work. And this is what people usually refer to as NLP, most commonly, but not always, and I'll come to that. So, okay, we said we are going to answer in which ways computers can understand and use natural language by building computer programs that show deep language understanding and language use behavior. The approach for building such programs today is based on end-to-end deep learning. Now, I know that neither machine learning or deep learning is unfortunately prerequisite for this course. So let me just go over what is deep learning. To know what deep learning is, we need to know what machine learning is. And machine learning is an algorithmic field that designs algorithms to make predictions from data. Again, this stands opposed to your traditional programming. When you are traditionally programming, you write the solution to the problem, right? Like you write if statement, for loops, and everything. And later, when your program outputs something, and if there is a bug, you can go back and change the line of code that likely is causing the issue. In machine learning, we write the code to train a model, but this model has some kind of parameters that are initially set to be random. And then we give data to this model, and the model iteratively, together with some labeled examples, is changing those parameters such that in the future, it can make right predictions for similar kinds of problems. So solution is actually patterns that are hidden in these parameters. And if they are not, the solution is not explicitly visible to you like the code is. So if there is a bug, it's way harder to debug your machine learning model. Deep learning is a subfield of machine learning where this model that I mentioned with its own parameters is a specific type of a machine learning model called neural network. End-to-end means that there is no human intervention about how this model is going to find the solution to this problem beyond giving it labeled data. So previously, before deep learning, in machine learning engineers and researchers would brainstorm what are the important features for this task. And then those features that we deemed important, we would check whether the given input has that feature. So for example, if we had a classification of dogs, maybe important feature is like, oh, has ears, has nose, or stuff like that, right? Now we don't do that. We give some kind of representation of that input, which doesn't require us to brainstorm what are important features, And then the model from that can still find those important patterns. And we're not going to focus on any kind of end-to-end deep learning model for NLP. We are specifically going to focus on large language models, which probably means something to you already. There are these general purpose, large-scale neural networks that have been trained on trillions tokens. Think about tokens as subwords or words that we find on the internet data, literally the entirety of the internet. And LLMs are an example of generative AI. There are other generative AI that LLMs aren't. For example, if you're generating images, those are not LLMs. So we won't talk about those. So now that we kind of progress from this first question into blah, 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 LLMs, and that's generative AI, your question that maybe emerges in your head is, oh, is NLP AI, is AI NLP? And I'll come to that. Before I move on to the second fundamental question we ask in NLP, are there any questions? Yes, please.
I'm sorry, watching a couple minutes late, but if I understand right, now we understand that natural language processing as a discipline seeks to answer the question of how computers can understand and use written forms or understand and use natural language. And specifically, you concluded that large language models are decisively one of a kind solution in this problem.
Yeah, it's like cutting edge emerging approach to building such programs. I want to say that they are almost like status quo for what they call highly resourced languages, meaning languages like English for which we have lots of data available. But there are over 7,000 languages in the world, and for many thousands of those, you simply cannot do anything with LLMs because their data is so underrepresented first on the internet and then by researchers actually building resources that were useful before deep learning or NLP. So yes, what you said is right with a small asterisk. I'm kind of focusing here in this course a lot on highly resourced languages, with the hope being that more such resources from unlabeled and labeled data will be built for other languages, and then LLMs will be applied for them too. Okay, so that's the first question we ask. The second question asked in NLP is to what extent can the properties of natural language be simulated computationally? And this is where NLP intersects with linguistics and cognitive science and psychology. You might not know that we don't really fully understand how our language, natural language, how do we came about producing it in a way we do. It's one of the scientific mysteries right now. And it's useful to actually think about linguistics as natural science. If you think about language being this thing we don't fully understand and the object we study it, you can completely think about it as natural science, like math. So if you take that scientific lens, language is the object of this study. We are trying to experimentally advance the construction of theories about our human natural language, and computational methods play only a supporting role here. So you have some kind of computational method, and you're not interested in building this computational method like we did for the previous question, where the method itself was the core thing we wanted to build. Here you're like, oh, cool, there is this method, and I can use it to understand how people produce natural language. Now, there is an intersect between the first and the second question. What you find out about natural language can be useful to then bring into your approach for building a computer program to see how your computer program can do summarization or translation or question answering. This is honestly less so these days for these high resource languages like English, for which this purely end-to-end approach where we don't give any kind of inductive biases about what natural language is are quite successful. So there is a less overlap today between these outcomes of these two lines of works, but maybe more so for other less resource languages. And today, while, when we say NLP, people think mostly, oh, you want to build a thing that can do process and use and whatever else, natural language. Like this line of work is typically referred as computational linguistics today. But keep in mind that this way of approaching NLP, where you learn something about natural language and then you bring it into your approach for building that computer program, was for a while the way we did the NLP. So our flagship conference, where the top tier NLP research is published, is called Association for Computational Linguistics. So computational linguistics is so out there, but it's mostly this NLP work that's being published there. And a lot of people will think these two things are synonymous because these questions have traditionally been deeply connected. Okay, so these are the two questions we ask in NLP. I did say I will kind of make a little digression about what's the connection between NLP and AI. To do that, I will just quickly cover a little context about what AI is today. So maybe actually it would be fun to try and see what AI means to you. Does anyone want to maybe give some definition of AI? And I would preface by saying that there is no right definition of AI, so don't be shy to say a wrong thing, because there literally isn't a wrong thing. Yes, please.
In my opinion, an AI is an artificial creation that tries to mimic human thought patterns.
Okay.
Using computers and software.
Okay. Mimicking human behavior, human patterns computationally. Okay, good. Any other definition? Yes, please.
I include decision making.
Decision making, great. I feel like, yeah.
Yeah, I would say it's more of a overarching field, kind of, where it's AI, then machine learning, then deep learning. And I feel like it's just pretty much pattern recognition, essentially. Machines trying to find patterns in data and then
finding patterns in it. Very good. Yeah.
I think in machine learning, the deterministic outputs, bring the variable regression, you're always going to get the same R-squared, you're always going to get the same coefficients, but when you're doing AI, it's generative, and you're assigning probabilities to certain outputs and choosing based on some schedule, which of these probabilities is most likely.
Okay, so some kind of modeling probabilities and randomness is involved in AI, mostly other kinds of models. Okay, this has been already pretty, you covered lots of bases. I will go over the historical context here, and then you'll hear a lot of definitions you have actually given me. So where it all started, it started in 1950s, where the phrase artificial intelligence was actually coined. And it was referred to this aspiration of realizing an entity possessing the high level or cognitive capabilities of humans to think and reason, basically aligning with your definition of what AI is. And I want to immediately bring a connection with NLP here. So language processing is one of the central features of our human intelligence, and therefore it is deemed as a prerequisite for AI. So if you want to build that computer program that mimics behavior of people, it should have the ability to understand and use a human language. On the other hand, reasoning is necessary for language processing. And just to give you here an example, there are two sentences here. The trophy doesn't fit in the suitcase because it's too small. The trophy doesn't fit in the suitcase because it's too big. Do you all feel like you understand what it is referring to in these two sentences? More in hand. This is like a basic common sense. Okay, raise your hand if you understand these two sentences where the it is referring to in each one of them. Okay, pretty good. Most of you do. So in the first sentence, we have the trophy doesn't fit in the suitcase. And if we because it's too small. What is too small? Well, the suitcase must be small here because we are trying to fit obviously something that's larger than the suitcase, and therefore the trophy can't fit. And in the other example, we have it referring to the trophy because trophy is too big and therefore it can't fit into something that's smaller, which must be the suitcase in this case. So this is one of the common examples of how you need reasoning to do language processing properly. Okay, so there is like NLP is needed for AI, and AI reasoning is one of the main parts of AI is necessary for NLP. I do want to go back to the definition. So in the last several decades, AI has become synonymous almost with machine learning. So you mentioned we have AI and then machine learning and then deep learning and so on. Although these are different things and one is subsumed in the other, these things we often refer to AI as it's machine learning. And when you bridge the ML experts, so people who are building algorithms with databases and distributed systems experts, you get something that we refer to as data science. And in the 90s, when Amazon has started, these things have been all kind of conflated with each other because data science was the prime example of like AI, right? So the focus shifted from producing entity possessing human level intelligence into something that helps people with decisions, such as giving recommendations of which product to buy on Amazon. And I believe some of you have mentioned, yeah, AI is decision-making machine, and you are not wrong by saying that. It is one notion of AI, very popular one, but not you know, it doesn't cover everything, every way that people use AI. And now in this era, you probably got a lot of like hype around LLMs and maybe some scary headlines about, oh, AGI is coming soon. So LLMs like ChatGPT have kind of started this discussion about human level intelligence again. So AI, a lot of times these days, is also referring to this notion of entity possessing human ability to reason and think. Okay, so that's a little like overview of how we use AI. So now going back to the question, is NLP AI, is AI NLP? My first thing I want to say is that it's even hard to think about this question because there is all these differences in how we use the term AI. But if we take the original, you know, focus on AI to as an entity having human ability to think and reason, then I said language processing is prerequisite to AI. Reasoning, which is kind of AI technique, let's call it like that, is essential for basic tasks in language processing. But NLP aims to answer other questions beyond creating such entities, such as how are two languages similar or different? You can computationally maybe measure that. Or how can we build technology, not that things and reasons, but rather is doing very specific, narrow things, such as it's just a translation tool, it's just summarization tool, and so on. And how can you do it in different languages? And then the question of how do we evaluate that technology? What does it mean for a summary produced by a summarization tool to be good, and so on? So my final verdict here is, and not just by me, I'm citing someone else here, is that NLP intersects with AI, but it's neither subsumed nor subsumes AI. So there are stuff outside of AI that don't, like motion planning, not super important for NLP. And there are these questions that we ask in NLP that aren't so important for general AI. Okay, so this is just a little kind of going over definitions, what is NLP, computational linguistics, AI, and now I want to kind of shift into what the focus of this course is going to be, kind of topics we are going to cover, such that you have getting a good mindset of what to expect in this course, and potentially you realize this is not what you are fully interested in. Again, any questions before we proceed? Okay. So, I maybe already hinted that we are going to focus on this first question. So, in what ways can computers understand and use natural language? And that's connected to building technology that actually can do such a thing for various language technology, summarization, translation, question answering. And instead of looking at every single approach there is and giving you like a historical rundown of how people did this, we are going to focus on large language models. So the first part of this semester is going to be focused on understanding in a technical terms what these large language models are. So we are going to go into the details, and then after the fall break, we are going to see how we can enhance them, use them and evaluate them for various language technology. That will mean that, for example, to build a very successful chatbot like ChatGPT, we need to change our base model such that it's not overly toxic and doesn't start to write hate speech all the time, because that's not the product most people want to use. So we are going to see what kind of technical addition we need to be able to do that. Or now, maybe you have heard that LLMs, when they are unsure, they will produce information that's not true given the known world, such as incorrect fact or something that's completely made up. We refer to this as hallucinations. So to build a very successful question answering system, we are going to add another technical component of retrieving from a database where the right answer might appear. So there is always going to be this connection between, we are changing something in an LLM such that we can have them perform better for certain language technology. So it's still going to be heavily focused on LLMs. Okay, and now I'm going to before I dive deep into the topics, this is maybe like interesting timeline of NLP. You can see already here how that it's been around for a really long time. It's not a thing that had started with ChatGPT. And initially here we had one of the most prominent events is the release of the Pentry Bank corpus, which is a corpus of English sentences with annotation, human annotation of syntactic structure. So saying this is a noun, this is a verb, this adjective in this noun make a noun phrase, and so on. And these syntactic annotations were very important for initial language technologies such as machine translation, which was one of the most, like the first emerging language technology to be researched. Here you have something called statistical NLP. This is where machine learning is becoming a big thing in NLP, so both for supervised approaches where you give label data such as support vector machines or SVMs, and for unsupervised approaches where you don't give label data. For example, topic modeling is one of the important examples of that. And we won't cover again any of that. So we are going to focus on basically 2014 onwards. These initial things in an early neural work in NLP, such as word-to-vec, word embeddings, and sequence-to-sequence approach. We are going to cover all of that because these are the building blocks to understanding what LLMs are, okay? But again, if you are super interested to hear about this grayed out area, unfortunately, we don't have time for that in this course. Okay. So since I said we are going to cover what LLMs are, I'm going to give you a little bit of information of what that means. So here we have a prompt and we have a completion of that prompt. Prompt is explain superconductors like I'm 5 years old. And then ChatGPT generates something. Our goal in the first part of this course is to understand what happens here in between you giving a prompt and receiving a response. So the first thing that happens is tokenization. We don't, when we build these models that process natural language, they can't process the entire string at a time, because that would mean we have an amazing representation that we can put into computer, meaning it's some kind of numerical representation for every single possible sentence in, let's say, English language, and there is infinite such sentences. So that's an impossible task. So instead, we embrace this idea that, okay, language, we have alphabet, we have words. Let's break the sentences into these pieces, and let's learn a really good representation of each one of these pieces and then combine it to do something. So that's why we do tokenization, which is splitting input into these units. Now, here you can notice, let me put this here. For example, superconductors, I'm sorry if you don't see color super well, but it is basically split into two parts, superconduct and then suffix ORS. So we don't take this full word, rather we split it into what we call two subwords. So although this idea of how to split input into these tokens has been around from already 1992, this is an ACL paper. This is still an active, ongoing research area about how to do this properly. So we are going to talk in this course how we split text into a sequence of tokens and which tokens we choose to be in our vocabulary. And again, as I said, this is an open area of research because it's really non-trivial to do this right, but it is the cause for many, many downstream issues we see with LLMs. So like the first step is faulty, and then everything else has no chance of recovering. So it's a really, really important topic. Once we have our tokenization done, and we map each one of these tokens to its vocabulary ID in the vocabulary, then each one of these IDs is going to be associated with a high dimensional vector. So I don't know how much you know about NLP, but I think this is very often when I talk to my friends who are like dentists and don't know much about how we build these programs. I think this is a very interesting idea that now you have a token, which is at most a word, and you represent it with this high dimensional vector that in 2018 was at 300 dimensional, and these days with open model it's 4,000 dimensional, and with ChatGPT it's probably, I don't know, making something up, but like 10,000 dimensional. Like it's a huge vector for just a single token, just a single word, right? So I find that idea intriguing, but we do that. And the way we do that is by embracing something, again, from 1950s called distributional hypothesis, which states that words that occur in similar contexts tend to have similar meanings. So if we think about vector space, we would like these high dimensional vectors of such words to be close to each other. And for words that do not appear in similar contexts, we would like them to be far away from each other in this vector space. And then you can use something like vector similarity to measure similarity of words, or if you aggregate all the words that constitute a sentence, similarity of sentences. Okay, so we do that. This is already what we have done in 2018. And then, for example, here you can see words that are related to kitten based on one of the models that's built like this on English Wikipedia. And you can see that puppy is a very, very similar word under this model, meaning we didn't measure exactly lexical similarity, right? Like puppy and kittens they have entirely different meaning, but obviously their relatedness is that they are small newborn animals of their, I don't know, adult parts. So this is something we'll cover in more depth. But then that's what we did in 2018 as a field. We are going to move forward. So now we had these embeddings for each one of the tokens. We are not going to stop there. Instead, we are going to allow each one of these high-dimensional vectors to look at other high-dimensional vectors and kind of decide, ooh, should I update this high dimensional representation based on what I see in other tokens? And the reason for that should be, okay, maybe it's too hard of a question I wanted to ask you, but the reason why we want to do that is because I told you that same occurrence of the same word can have different meanings in different contexts, right? So if here the vector of Bayesian can look around and see, ooh, what are other words in this sentence? It can see, well, oh, I'm anthropomorphizing this, but let's say engineers are doing this. Then we as an engineers can update this representation based on the context and basically disambiguate this word such that we use the proper sense of it. So this is what we do, and this is the key ingredient of the neural architecture you might have heard of called transformers, which has a mechanism called self-attention, which allows this process. Again, this is now, I understand probably a lot, and you don't need to understand most of what I'm saying, but you should get the sense of, oh, I'm gonna learn about this, and I'm gonna learn it in a detail to the point that in my third assignment, I'm going to implement this from scratch successfully. So that's what we are gonna do. We also want, we will do another change with these high dimensional vectors. We are basically going to do deep learning, right? Which means transforming these vectors non-linearly. And here I'm going to give you a standard motivation for deep learning that I give anytime I introduce deep learning. So here you have linear classification, meaning here we have a blue set of dots that are of some class, let's call it blue. And then you have red line of examples, which represent some other class red. If you would like to use a linear classifiers, which means you can only draw lines as the decision boundaries, that's at most you can do, you will always have some loss of loss of your decision accuracy. So here, these points will be classified as blue, and these will be also classified as blue, and these will be classified as red, which are all wrong decisions. So to classify this problem successfully, you need something that looks like this, but that's not linear function, right? That's non-linear, probably something like quadratic function. So what we do with deep learning is instead of trying to find this complicated function, we transform each one of these examples that lie on the blue or red line. We transform them such that we can use linear function to separate these set of examples in this new transformed space. So here you have a linear function separating these two now bended lines. That's the idea of deep learning, transforming your vectors into this hidden or latent feature space, and then doing linear decision-making there. And that's what we are going to be doing as well with our high-dimensional embeddings. All right, so far we had prompt, and we ended up with a sequence of high-dimensional vectors that are contextualized with respect to each other, and they are non-linearly transformed. Just to see whether you're still with me. Why are we doing this? What is our goal? Yeah.
Can you walk through the map words in relation to each other?
A little bit low level, like where did we start? What do we want to produce?
Output based on.
Yes, output based on a prompt. Our goal is to generate the response, but now I have created a sequence of high dimensional vectors. So your question can be, hello, like how do these two things connect, right? So once we learn how to do all of that, we are going to then see how we can generate the response. So imagine, I didn't go into details of this, but with deep learning, you have basically composition of these nonlinear transformations, and we call these layers. So finally, you reached your final layer. You don't want to transform your vectors anymore. What you do then is take the high dimensional representation of your last token. Let's say period was our last token. We take its high dimensional hidden representation coming after all the transformation, And the reason why it's efficient is because of that contextualization. It kind of knows everything about all the tokens that preceded it. Now, I'm going to get a bit more technical just for the slight moment. If you have taken machine learning or deep learning, this will be completely clear. If not, you won't fully understand it, but that's okay. So here is our high dimensional representation of the last token in the prompt. And we are trying to predict the next token. That's our goal. So the way we do this in machine learning is to linearly transform this vector into a vector of the size of our vocabulary. A linear transformation is always going to be just a multiplication with a weight matrix of a certain shape. And once you have that vector of the size of the vocab, you're going to apply a function we call softmax to squish all the values in this vector between 0 and 1, and such that the sum of all the values sum to 1. What kind of concept does this remind you of?
A probability distribution.
Perfect. Probability distribution. It's not exactly probability distribution. We like to say it is, but it doesn't have, for example, these things won't be confident, probably calibrated in their confidence because it's not probability distribution, but we are trying to mimic probability distribution by doing this. So once we have here values that are something like probability, and my goal is to predict the next token. What could I do? So I have these probability values and I'm trying to find next token. What's a simple thing I can choose to do here? Yes, please.
Choose the most likely one.
Perfect. Yeah, choose the most likely one. Why not, right? And this is called greedy decoding or greedy search. And the issue with greedy decoding, with like any greedy anything, is that you can get trapped in these locally bad decisions, right? So our goal in this, when we come to talk about this, is to learn how better we can choose next token based on that probability distribution. And instead of choosing this deterministic approach, we are going to sample from this distribution, and we are going to learn something called top P sampling, where basically are going to take the few most likely tokens that together have a probability of some threshold you set to, let's say, 0.94 here or 97. And then giving only that choice of tokens, you're going to sample from them. And this is exactly why for the same prompt, when you use ChatGPT, you don't get the exact same answer, right? Like sometimes you get different because there is some randomness that you mentioned before involved here. Okay, so this will get us from, okay, this is how we actually sample next tokens. I said that these base LLMs won't be perfectly good for everything what you want to do. One thing that we're going to learn likely before the full break, although I'm not 100% sure, is this idea of pre-training. So instead of starting from randomly initialized neural network and then training it for the tasks such as summarization, translation, whatever, we are actually going to do pre-training and then fine-tuning the network. Meaning, not us, like corporations like Google, OpenAI, Anthropic, Meta, and then open institutions that release open models like AI2 and so on. They will do pre-training by taking a randomly initialized network, taking a scrape of the internet, and then predicting what the next token in the corpus is. They are going to build a neural network where weights are no longer randomly initialized, but they are tuned to be good for the language modeling task, this next token prediction task. And then they are going to upload it to Hugging Face, and us will download it, and then we might have label data, and we can fine-tune it, meaning further train it for this task, or maybe we can just prompt it, meaning we don't even fine-tune it. Here, we are going to learn two ways how to go about pre-training, then fine-tuning. I won't cover this now. But this is a point where we get this LLM And now we can apply it to build many kinds of language technologies, right? I told you that our goal is to learn one of these approaches of how to build those computer programs that can use and understand human natural language. This is going to be the main approach we learn. So once we learn how to do pre-training and fine-tuning, we know quite a lot already. But then I said, this won't be enough. And then we are going to learn how can we make LLMs follow any instruction? How can we make them not go rogue, meaning like they don't spit out toxic text and hate speech as soon as you write anything? How can we efficiently use them on GPUs, or how can we efficiently generate these tokens, especially if we have very long context? How can we avoid these hallucinations with systems like RAG? And then how do we actually apply them for all these different language technologies and evaluate them for this task? We are going to talk about all of that. Okay, so I want to go over course logistics now, but are there any questions? Yes.
So, when we're applying our token to the token matrix, it's after contextual embedding, right?
Yes, so you produce for every single input token, a high dimensional vector that's contextualized, meaning it's updated based on the information that's present in other tokens in the input. And it's also non-linearly transformed such that we can do these better decisions later on. Yeah. Yes.
These pre-trained models you talked about, are they effective at generalizing linguistically usually, or how do those?
Yeah, that's a great question. So the way that we call it being like multilingual LLMs. The way this is typically achieved is by this corpus you take for pre-training. It's not only specific in one language like English, rather you have a mix of data from multiple languages, like 100 languages is very common, which is still nothing compared to how many languages there are, not to mention dialects. And then you basically do everything kind of the same. You need to be careful with the mixture of the data. If one language is too overrepresented, then it's going to be too good for that task and so on. And there is evidence right now that even our best multilingual LLMs are still defaulting to English. So you might have heard about reasoning models like OpenAI's O1 or DeepSeek's R1. These models, when you look into how they are generating those thinking tokens, we can see that they are basically doing something in English and then reverting back to other language, which is not ideal. Yeah, so it's a very active area of research how to build proper multilingual models. Yeah. Yes.
Were the DeepSeek and other international models trained on English?
Yes. Yeah. English is the most researched language you have. And there is evidence that if you learn something from one language, it's going to transfer to another because there is a shared syntactic structure, like how we structure languages in certain language families is not widely different. So if you already have learned something about grammar of one language, and let's say English, and now you have some German data, and I'm trying to apply there. Okay, German is not a very good example, it's terrible. But let's say we take Swedish language, then that's going to transfer a lot to the target language that you maybe didn't have found data for. If languages are widely different, then this it doesn't work necessarily so good. Yeah.
Like they would be the same, in the same place in the embedding space, but with different labels.
So yeah, that's a good question as well. It all comes back to those tokens, right? So those tokens, if I start from a corpus that's multilingual, I'm going to learn from this data what the good tokens are to include in the vocab. And then I will have some tokens there, which are subwords, and I can compose words that are English words, but also maybe Croatian words from these tokens, right? So there are like smaller units than words, right? So to kind of come to your question, your question was about these high dimensional vectors. You will have vectors for these subgroups, and the way you combine them will be length specific. I mean, we won't define it as engineers again. The model will learn combine it. So, yeah. Yes.
Yeah, I'm just wondering if the English is the most efficient language to to train the model. I'm just thinking, like the example you gave, like maybe transport to like other languages, they might have like less issues on like the ambiguity problems. So maybe, I mean, maybe possible. Are there maybe other language that more efficient? English?
Yeah, I mean, by more efficient, it all comes back to amounts of data you have, right? But it's an interesting question you pose. Like in theory, if we had lots of data for any language, what would be the most transferable language, right? That's a very interesting idea. I don't know what that, like which language would that be. But yeah, right now it all comes back to resources, right? I mean, English is not the only highly resource language. A lot of data for Chinese or Russian. There are Spanish. There are a lot of data for other languages as well. But then again, that's just such a minority from all the other languages there are. Yeah.
Is this a really sorry.
Yeah, maybe
So I sometimes use the graph or Gemini to try to visualize a model to some like other language content, but it always feel like it's still like translate to the English first and then
Yeah.
convert to the other language.
Yeah, no, it's definitely doing that. So what I kind of was mentioning before, if we do some of these interpretability methods and we look into hidden representations at various layers, we can see that it starts from, let's say, French, and then in hidden representations, it's most active for English tokens, and there is really no reason for that to be the case. And again, like we definitely know that there is some defaulting to English happening, but we don't fully understand how and how to prevent it.
Thank you.
And I just was wondering, like, does this process that we covered apply to like images as well, or is that just a completely separate process that's going on?
Oh, that's a good question. It's everything kind of is looking the same these days. So we have this transformer architecture, which is the state-of-the-art architecture for vision processes as well. But crazier to me are these tokenization procedure. Vision community can kind of mimic something similar. So we have an image, and then image is divided into patches. So you have an image like this. This is your image, and then you divide it into patches such that you have 9 patches. And then each one of these patches is first vectorized. Basically, you can imagine taking columns and then putting them stacking them one under the other. And then you transform this vector into something that's slightly smaller and manageable. And then from each one of these patches, you get a sequence of vectors, right? And so on, which is exactly what we get as a starting point with language, right? Like there we have a notion of token being completely different from a patch, but where we end up is a sequence of vectors, which is then processed with a transformer in the exact same way. Yeah, so some people are very happy because of this, because everything is unified, so you can have vision and language models, right, more easily built. But then there is also a question, well, we know these are quite different modalities, so should we really model everything exactly the same? But the reality is that transformer architecture takes a sequence of vectors, and transformer architecture together with some data, lots of data, is a great recipe for scaling. And scaling has been associated with all these downstream benefits we have had. So if you have a successful recipe, like why change it, right? Like I think as a research for sure, but if you're a company building this, it's easier to bet on a successful recipe than trying to risk trying something else.
With this site you're referencing right here, is this like a pooling layer or is this something separate from like a pooling layer? Let's see.
It's slightly different. So here, basically, we produce, let's say we are thinking only about black and white images, so we only care about the intensity of black color. So each number here is the value of black color for a pixel. So if you look at this patch, we need to produce a vector just to be able to transform it. So you can do it by stacking columns vertically, but then you'll get something that's large and weird and you don't want that. So you want to, usually you just linearly transform it. And again, linear transformation, you will hear me talk about this a lot, is just a vector matrix multiplication where this matrix is of a certain shape and it's learned matrix, right? So you learn a good projection this vector. Yeah, but there is no pooling as far as I know. Yeah.
I'm kind of wondering, since like English is more like semantically similar to programming languages, just in the sense that you're using words like if. And especially in like database languages, if training it on English would make it better at programming, or if it's like they usually train models for programming on like exclusively code.
Okay, I see what you mean. I mean, yes, you use if and when, but that's the structure is more important. So I would say it's some signal, but it's not a crucial signal. Just knowing that it means whatever, you know, it's a shared meaning of word if. What people do today is that mix of pre-training corpus to have code data. You have English data, you have other language data, you have code data. And the way you produce code is the same way you produce language in these models. You just predict what the next token will be for producing the code. So it's just about how you graph this pre-training data. It's not super intellectual simulating, but it is how this is built. Yeah.
So does that mean that these procedures of natural language processing could be used for these non-natural languages, like programming languages?
Yeah, I think I'm not saying this with 100% confidence, but this mixture of natural and programming data has benefited both natural language processing and obviously code generation, because you need, you know, code to generate code, but also having some natural language, for example, due to comments people keep in their code has been beneficial for the code generation as well. I think there is one paper that showed the extent to which just purely code data helps language processing, and that was very intriguing result to me. I didn't expect that so much structure can help, like structure in a programming language can help processing natural language. Yeah. I'll try to, let me make a note. Okay, I'll write it on the whiteboard. So what did I say? We talked about, so this code data to natural language processing, and then the other paper I should share you is the one on defaulting to English. Okay, I'll try to remember to share these two with you. If I forget, just send a message to Piazza. Yes.
Question. So, for languages which are like indigenous languages which have very low data resources for them, I have seen a few LLMs or some GPTs created for those based on just a small amount of data. So, for such kind of LLMs, because they're trained on very a small set. Do you think the more times we train the model on that particular set of data, it can understand the natural language modality in a better way? It can can it understand the conversation that a person would let's say if it's a voice-based LLM. So if I say a sentence thread in the language, would it be able to understand it better because we've trained it multiple times on the same set of data?
Yeah, the challenge there with we do typically in this I said to build multilingual LLM, you need this corpus with multiple data from multiple languages. But the issue is that some languages are so underrepresented. So you might be thinking, oh, I should make all the languages having the exact same amount of data such that one is not overrepresented, but then your data becomes too small. So typically people do oversample the same sentences from the low research data. The issue there is memorization. The more the model sees exactly the same example, is going to repeat it verbatim. And that's a huge issue, especially now when we have questions of copyright in place as well. And in point to memorization is kind of associated with not generalization, doesn't really understand, if you give a slightly different prompt, it might still give you exact same memorized sentence where it should have adjusted just a little bit. So yes, we do some, oversampling, but then you need to be cautious with the memorization as well. Yeah. I don't know who raised their hand first.
Go ahead.
When you're training on that large text corpus, what's it actually doing? Is it taking like counts of words following other words or?
No. So basically process I have just showed you, right? So you have this large corpus and it's typically not just sentences. Imagine that's more like paragraphs. And we start with something like, so there is a difference between training this model and the inference, right? So I'm going to talk about training. Here you are going to do what I told you, like have the tokenization of the input and then these high-dimensional representations. You are going to transform them, and at the end, you are going to have the distribution over the whole tab and moving to the next one. So there is no notion of like counting explicitly. The model might be doing some counting, but it's not explicitly programmed. Yeah. So the recipe is the same. You just your pre-trained corpus looks different and it has all these different languages, but what's happening after that is the same. So you ready to?
Yeah, I was just gonna say for like a problem like that, or just like only like a small corpus text for like a certain language. Couldn't you do like translation and then sort of like synthetic data generation from those translations? I know that's being like done a lot, like in English is like the synthetic generation of training model, just purely synthetic data.
Yeah.
Something similar with like just like small corpus of text.
So when we come to the point where we talk about instruction following, this is where people do translations of English data. I don't think they do it for the basic training. The biggest challenge with translating, first of all, you might think we have a great translation tool for everything. We have it for hundreds of languages maybe. And again, these low resource languages are not then going to be languages for which much translation tool is done. It's the exact same problem for building a translation and building an LLM for that language. Even if you have a great translation tool, there is the differences in cultural aspects. So in English data, especially from the North American region, you will find a lot of mentions of like Super Bowl and I'm European. I don't know, like that doesn't mean a lot. So when I get, even you will learn a lot about some cultural aspects that are not so relevant elsewhere, then you get this mismatch, and you might have some cultural aspects of that place that you completely miss with your English data. So, but the biggest issue is translation. Translation works only for a small set of languages, and not those for which we want to improve this. Okay, let's maybe jump into logistics. I'm super happy to see this many questions. I feel like, okay, cool, then you want to learn what LLMs are, because it's always a little bit tricky to choose what the NLP course is going to be, given that, as you can imagine, it's just rapidly changing. So I made this decision to focus on LLMs, but I know some of you might be interested to learn some other aspects of NLP. Okay, so let's go a little bit over the syllabus. First of all, I want to say I'm not going to read this syllabus here entirely, and it is your responsibility to read it and be informed with everything that's written there. So please do read it. I try to keep only important information. So yeah, here at the top, you can see a little bit of overview about course staff. I did write my office here. I would ask that you show up only by appointment. This stems from some incidents that have happened in the fall, which make me still stressed to have you unannounced in my office. So please, for my mental health, just shoot me an email to meet with me in my office. In terms of the office hours, I'm going to send after this lecture a little poll on when are good times for you, basically times where you don't have major conflicts such as other lectures and maybe your TA for other class. Because once we had set office hours and then turned out that those times don't work for most of the students. So please fill that when I send it later. Recordings will be shared on the YouTube data science channel. But keep in mind that this isn't an online course. I think it's helpful for you to have recordings such that you can, you were here and then you want to check, oh, I didn't quite get some part of what I was saying, and it's nice reference point. But sometimes recording just fail, and then you rely on your peers to share notes with you. The slides will be available on the webpage. So the webpage is organized like this. So here you can see I typically put slides before lecture because I know some of you use iPad and you like to make notes as we go. So most of the times I put slides just right before the class, and then recording and some readings will also be shared over here. In terms of readings for your exams, I will ask you only about stuff I have talked about in lectures. So slides are the thing you must know and everything that was said in the lecture. Readings are mostly, oh, I want to maybe read a little bit more about some stuff, or maybe I'll share a chapter of a textbook that's available online that you can read to kind of have a lengthier version of what I was saying. All right, so let's jump into communication. All communication will happen on Piazza. Here I put you a little table to give you, I don't know, guidance of how to reach out. Most of the times you will be using Piazza, and then sometimes there are some urgent stuff that you will email me about. Please, if you can, remember, put this thing at the top of your email, because I get a lot of emails, so it's going to be easier to recognize your email among all of them. I personally don't respond in the evening. I don't expect TAs to do that either. I don't work over the weekends. I don't expect TAs to do that either. So reach out to us if you need us during the work hours. If you need to have an appointment with me or TAs, please give us a little bit of space to organize that meeting. Sometimes I get an email, hey, can we meet in an hour? And I wish you can see my schedule because that's impossible, right? So if you need to meet with us, you can't make it to the office hours, super happy to meet with you, but be realistic about us having a whole other set of jobs next to teaching. So we will meet with you, but we need to find time in our schedule that works for that. You can post anonymously to other students, but your names will always be visible to me and TAs. And I think that's it in terms of communication. Any questions about communication? All right. Okay, so maybe something that you will be not super stoked to hear, but the way the programming assignments will be organized is in two parts. One part will be ungraded and the other part will be graded. So I will release assignments and you will work on them. You will have 2 to 3 weeks to work on them. And you will submit your solutions to Gradescope, but we won't grade those solutions. We will use them later for analyzing what are you doing, but those won't be graded. And then 2 days after, we are going to meet here, or I will try to split you in half and then have 2 rooms. And you are going to receive a coding assignments. You will be asked to bring your own laptops. If you do not have a laptop, please check out, and share here a link, a library can give you one. And then if you run into any issues with having a laptop, please reach out to me as soon as you can. So we'll meet here. You're going to get a programming task very connected to what you were programming in your offline. And that part will be graded. It's going to be set up to be realistic. So we'll have our 20 minutes. I won't give you something that you can program just in our 20 minutes, of course. You will have time to program it, but you won't have access to internet. I will give you, if you need some torch function, I won't ask you to memorize it. I will give you description of functions you need. So you will have, if you have coded your programming assignments and you come here, I know this is always stressful, but with plenty of time, you will have good chance to have high scores on these proctored versions of assignments. So that's the biggest change in evaluation from previous years. Exams are basically multiple choice questions. I would say they are easy, but that's not what the scores show. And I think the scores are very correlated with who comes to lectures and who doesn't. I don't take attendance for lectures. You have to be here for these proctored versions of assignments and exams. Otherwise, I won't keep track of whether you're coming. But if you can, come, because I think it benefits you for the knowledge part of the assessment. Or if you are rather want to rely on recordings, I hope you have a good time management and accountability that you actually look at those recordings, because I think there is a sense of, I'll be checking recordings, and then 3 recordings are uploaded and you are behind. So attendance is mandatory for these practicums and exams. So you must be here, which means that you cannot now make travel arrangements when I expect you to be here. This is a common problem. I don't know why. I think after COVID, maybe we had the sense of everything is remote and we can travel a lot. So travel for me is not a good excuse for not coming up here. I get it. My family also lives in another continent, and I wish I could be there sometimes when I cannot, but I have a responsibility to show up here, and I expect the same from you. Undergraduates will have some accommodations. I put this under accommodations. So the way I'm going to do these exams is basically portion of questions will be extra point for undergraduates, but not for graduate students. And I'm going to drop the lowest scoring programming assignments for undergrads, but I will still expect you to have a bonus track. So not showing up and getting like intentional 0 will not be what I will consider for dropping the lowest assignment. Yes.
For the the ungraded assignments, is there any way to know how correct they are before we come to the?
I will set up for the first 3 an autograder. For the 4th one, there won't be an autograder. Yeah, so you will know correct. Yeah. Sorry, I think there was a hand there. No, just yeah.
So the second assignment, the one that's being proctored in class, that's going to be done the class after the first one is due.
So basically here, I can show you you can see it here. So for example, here it's a little bit exceptional because it's Monday is a holiday, so I put it on Tuesday, but typically on Monday, midnight, you have ungraded portion deadline. And then on Wednesday, next Wednesday, there is a graded portion. Yeah, so you have we'll set up some office hours on Tuesday and Wednesday morning such that you can maybe also check whether you have any kind of concern about, oh, I didn't quite get this part, and can we maybe walk through it. On that note, another difficulty with this course is going to be that we will not look at your code directly. This immediately leads to just us giving away the answer. It doesn't promote learning. So you are going to talk with your TAs and me, like, oh, this is what I'm doing, this is my pseudocode. We are going to, through conversation, lead you to the right solution without giving it away and answer. Sometimes, in very rare occasions, a student explains everything well and everything seems fine, and then sometimes we will look into the code because we literally don't know what else could be wrong. We don't have any suggestions for how to help them. So, something strange is then going on. So sometimes, very rarely we'll look at, but be prepared that we won't look at your code almost all of the time. Okay, let me just finish with, again, please read the entire syllabus, but I do want to make a note on prerequisites. So here's the thing. This course was taught completely differently before I took it over in spring 2024. It was all that grade area. This was NLP before, and now it's completely different. And now it's more connected to machine learning and deep learning. I will still cover everything you need to know for machine learning and deep learning. It's just going to feel fast. But I can tell you that the best students I had didn't take machine learning or deep learning. So you can still be successful. But if you're in that situation, it really depends on your stress management, I would say. Please read this, and then you need to decide for yourself. So yeah, please read this if you have any questions. I'll stick around after every class for a little bit, and then we'll have office hours organized really soon. Right, thank you.